Hydrogeologic provided an optimal design for a dewatering program at a mine site in the Pilbara region of Western Australia. The mine is less than 100 kilometers northwest of Tom Price. It is an open-pit mining operation with a capacity of tens of millions of tons per annum of sellable ore product, and has been in operation since the mid-2000s. The mine consists of 6 lenses of mineralization in the Mount Newman member of the Mara Mamba Iron Formation. The lenses stretch from east to west for approximately 14 kilometers. Green zones represent the mining lenses, and orange zones are stockpile areas. Dewatering borings are initially constrained to be outside of the green and orange zones. The mining industry is increasingly faced with the challenge of extracting natural resources accessible only by mining below the water table. HGL's Physics-Based Management Optimization, or PBMO tool, was pilot-tested on the mine to assess its applicability in this dynamic environment. The mine floor was scheduled to go below the water table in the near future. Numerical groundwater flow models are used in developing mine dewatering strategies, predicting dewatering extent, and assessing abstraction rates and effectiveness. The standard practice for determining dewatering bore locations and abstraction rates is for experienced hydrogeologists and engineers to perform a few well-thought-out scenarios with the aid of calibrated groundwater models. The client requested HGL to deploy its PBMO system for optimizing the mine dewatering program for a lens in the middle of the mining area, or lens CD, and to compare the results to the subjective engineering judgment developed solution. Locations for candidate water abstraction borings and exclusion zones were provided. Lenses CD has an area of approximately 2.4 square kilometers, or approximately 600 acres. 113 bores, comprising of 100 ex-pit bores and 13 in-pit bores, were supplied as candidate bores for PBMO to optimize. The ex-pit bores were scheduled to commence operating before the mining was planned to go below the water table, and the in-pit bores can be scheduled to be activated after 4 years of mining occurred, at which time the area would be available and accessible. In-pit bores installed at lower elevation were required to advance the dewatering due to constraints on bore depth. Subjective engineering judgment was used to develop a dewatering strategy requiring 26 abstraction wells to meet the mining schedule. HGL's PBMO Optimal Mine Dewatering tool is designed to find optimal solutions to dewatering challenges systematically and effectively. We use our ModFlow Surfact, a 3-dimensional variably saturated, mass-conserving calibrated flow model, combined with our PBMO Global Optimal Search strategy. The fully calibrated model for lens CD was provided to HGL for analysis. The PBMO optimal design requires a total of 17 individual bores, with no more than 11 abstraction bores operating at any one time. The subjective engineering judgment approach applied for slightly different constraints in mining operations used a total of 26 bores, 18 ex-pit bores, and 8 in-pit bores. The following is an animated illustration of PBMO optimal design in action. The PBMO solution begins with 11 ex-pit wells, and the interior of the mine is unavailable for dewatering access. The blue surface is the water table, and the mine elevation over time is shown by the discs on the tracking points. This configuration operates for the first 4 years. PBMO then switches the dewatering strategy to consist of 5 ex-pit and 6 in-pit bores on year 4, and then complete the dewatering using just the 6 in-pit bores and 2 low-flow sumps operating. The mine elevation never goes below the dewatered water table. The PBMO total maximum abstraction rate is 55,000 kiloliters per day, substantially less than the subjective engineering judgment solution. Dewatering occurs at this maximum stable rate for the first 3 years, and steadily decreases thereafter as the sustainable yield from the aquifer decreases. Benefits of the PBMO optimal design versus the subjective engineering design include the following. Substantial savings in abstraction well bore installation costs is realized. Estimated savings is $500,000 for each of the 9 wells installed. significant reduction in peak flow rates and total volume of water abstracted. Estimated cost savings is $4.6 million. All abstraction well locations comply with restrictions on well placement. And all groundwater levels comply with mine schedule requirements. In summary, the computational efficiency, accuracy, and robustness of PBMO, combined with our ModFlow Surfect groundwater modeling software, has been successfully demonstrated on production-scale deep watering projects. This mining dewatering project consisted of 129 square kilometers of land area, which used multi-stage deep transient dewatering wells. To solve this challenge required a groundwater model with approximately 209,000 model cells, and a strong, robust, and stable transient groundwater flow code, capabilities only available in HGL's ModFlow Surfect. The problem was highly constrained, consisting of 113 water extraction decision variables per management period, and 178 time and depth varying constraints at 17 monitoring locations over a 12-year period. This optimization configuration incorporates the management preferences, the mine pit shell specifications, and the physical access limitations inherent during construction operations. Previously, projects such as these could only be tackled using subjective engineering approaches, and those approaches could only produce suboptimal solutions. PBMO reduced both the cost of this mining project and the amount of the natural resources that would have been wasted compared to the planned solution. The PBMO optimal pumping strategy and subjective engineering pumping strategy are compared in the following graph. Notably, the PBMO design reduces the total groundwater extraction volume by 15.6 gigaliters, or 4.1 billion US gallons, over the 12-year duration.